because when j is 1, I have 3 to the first power. When j is 2, the sum says plus. 3 to the second power, the sum says plus, dot, 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 till the last one, the upper limit is n. Awesome. Okay, let's look at one more. 1 to the third plus 2 to the third plus 3 to the third plus dot, dot, dot plus n to the third. Let's use k this time. Doesn't matter.
Lower limit would be lower limit will be 1. Upper limit is n. And the part to what's the part to the right called again?
The general term.
That was called the general term. The general term would just be k to the third.
It will be k to the third. Excellent. Excellent. Perfect. And now you can say, what are you talking about? Why are you doing all this? And here's why I'm doing it. Number one, there are 4 identities that you need to remember or have handy for the test and final exam. Here is the first one. The sum of 1 from I equals 1 through n is n. 1 plus 1 plus 1 plus 1 plus 1 plus 1 plus 1, n times is n. Here is the second one. There are 4 identities. This is the first one. I equals 1 through n from I, which is 1 plus 2 plus 3 plus 4 plus n. That is n plus 1 divided by 2. 2 more. The sum of I squared from I equals 1 through n. That is, this one is the most, if you want, cumbersome. n plus 1, 2n plus 1 over 6. n plus 1, 2n plus 1 over 6. And the last one is I to the third from I equals 1 through n is this squared. n plus 1 divided by 2. All these can be proven using mathematical induction. So we can prove any of these. We are not required to. After class, if you want to stay, we can prove together any of this. But I would like not to take the time unless you want me to. If you say no, I want to see how at least one of them is proved, then we can do it. Okay. So I could not explain what these meant without simple exercises with the sigma notation. I couldn't just give this to you and say, this is it, take it or leave it. So I had to explain how sigma notation is used. Number 2. Sigma notation has 2 properties. As you know, every time we invent a notation, it comes with properties. So here is a condensed property. So the sum from I equals 1 through n from ai plus bi, these are 2 generic terms, added or subtracted. No, we're not distributing this notation to it, but it's the same with the sum from I equals 1 through n from ai plus or minus, depending on what we have, the sum from I equals 1 through n from bi. Same thing with the derivative. A derivative of a sum of functions is the derivative of the first plus the derivative of the second. The same thing with the limit. the limit of this function plus this function, if the limit exists for both, the limit of this plus the limit of this. Doesn't mean that we distributed the symbol, right? When we differentiate, we get the same thing. When we find the limit, the same thing. With sigma notation, the same thing. And of course, the other property is the same as we had it for derivatives, the same with the limit, is the sum from a constant times AI. Of course, what do you think will happen to the constant if it's a factor? Exactly with the limit, exactly with the derivative. What did we do with that constant?
Does it stay or does it move to the front?
Exactly. In all cases, that's what we did. Okay. Any questions on this so far? Now
Is it okay if I use X instead of I? Because it does make things a lot easier.
No, when we write it, we cannot. Only in the calculator.
Okay.
Yeah, I'm sorry about that. The index has to be I, J, K. Yeah. Because we are going to have functions with X. And that's why we cannot use the index to be X. So you're going to see how we apply this for functions in a few minutes. So if I use the index X here and I have a function to multiply, then it's going to be a total mess. Very good question. Thank you for asking that. Okay, so now here is why we just looked at what we just looked at. We want to find or approximate first the area under f of x. Very simple example, x squared, on 0, 2. Of course, between the x-axis and x squared. And the question is why? Why would I ever be interested in finding the area under a graph? Who cares? So here's my graph. 1, 2, 1, 2, 3, 4. Here's the graph. And I am asked to approximate this area. Why? And who cares? Well, here is why. And then we'll get into details. If x squared is the velocity, if this is my x squared, y equals x squared, this is what I graphed on the interval 0 to 2. If x squared is the velocity, this area, total area here, becomes the total distance covered between 0 and 2. 0 minutes, 2 minutes, 0 hours, 2 hours, I don't know. It doesn't matter. The total distance covered. Okay, by anti-differentiating, basically, and finding this area, and we'll have techniques to do that, 2 different techniques, one very cumbersome and one very much easier. So that's why we are interested in finding the area on the graphs between the x-axis and the graph. If this is the velocity, the total area will be the total distance covered by the particle, by whatever, between 0 and 2. So now, what are the ways of determining this area? Okay, we have several, and we're going to study 3 for now. but there are others in Calc 2. So again, approximate the area. We will use so-called leftmost point. Second option, rightmost point, and midpoint. Of course, these three will give us different answers. And let's say for now, n number of subintervals is 2. So my first presentation will be n equals 2. Then we will look at n equals 4, and then 8, and then 16, and then 32, and then infinity. Okay, don't anticipate anything. Let's just look at n equals 2 and analyze these three options of finding the area. Okay, back to my graph. Here's my graph. So this is 0, this is 1, and this is 2. N equals 2. Now, the width of each subinterval is one of our best friends from the past, delta x, b minus a over n. b minus a over n. N is the number of subintervals. A and b come from the interval. In our case, the interval is 0, 2. The width of each subinterval, delta x. In our example, will be 2 minus 0 divided by 2. Delta x, 2 minus 0 divided by 2 equals 1. First, I have to establish the width of the interval, of the subinterval, and then I'm starting with the leftmost point. Okay, so here's the leftmost point, meaning the height is here, because that's what the height is 0. Base times height. Base times height. It happens that this is 0. Why? So the area with left to area leftmost point with 2 subintervals is delta x, which is 1, times f of 0 plus f of 1. Base 1 times f of 0 plus base times f of 1. Do you think that this number will be an overestimated or an underestimated area?
Under?
Grossly. Absolutely. Look, I'm missing all this. So this will be an underestimated area.
How did we get the AL2 equals that again?
Base of this rectangle times the height, plus base of the next rectangle times the height. 1 times f of 0 plus 1 times f of 1. F of 0 is 0. F of 1 is 1. 1 times 1, I get 1. Same graph with the rightmost point. For this base, this is the height. For this base, this is the height. So then the area with right to is base times height plus base times height plus base times height. So delta x outside, f of 1 plus f of 2. F of 1 is 1, f of 2 is 4, 1 plus 4 is 5 times 1. Good. Let's look at the last option here. Midpoint. Midpoint. I forgot to ask. Underestimated or overestimated?
Overestimated?
Over, of course. Grossly. Look at this. The area with midpoint 2, base times height, plus base times height. Is this the best estimate, you think? Do you expect it to be a number? Of course, it will be a number between 1 and 5. Okay, f of 0.5 is 0.25, and this is 2.25, and this is 2.5. From all these three, which one do you think is the best? Of course, you will say the midpoint. So the midpoint gives us the closest to the true value. Correct area. Okay, so now just let me illustrate. I'm not going to calculate anything because we have enough. But let's say I want 4 subintervals. Let's say I'm using the rightmost point, base times height, base times height, base times height, base times height. Then I'm going to use 8 subintervals. And then I'm going to use 32. And then I'm going to use etc., etc., etc. So with 2, yeah, I got 2.5, the closest I could. With 4, do you think I'm going to get a better area? Closer to the truth?
Yes.
What about 8? What about 16? What about 32? What if I have infinite? They're infinite subintervals.
Would that make it exact?
That will make it exact. What concept is that? When n starts with 1, 1 is too small in this case, but 1 could be 2 and 3 and 4 and 5 and 6 and goes to infinity. What concept is that? Have we ever seen that before? Have we ever used that idea before? When something goes to infinity?